Okay, so we are going to try to do a lecture on video. This will not be at the midterm, but with the campus being closed, we need to keep up with the schedule of Physics 9B. You can also read this in the book, right? This is chapter 18, but I thought that a video might help. Now, I hope that everybody is feeling okay. I am myself feeling a little sick. I don't know if it's because of the smoke in the air from the campfire or not. This surely doesn't help. And so this video, I have never done that before, so forgive me for the style. I'm using my wife's iPad and an Apple Pen, and so we'll see how it goes. And so last lecture, we have seen that the average translational kinetic energy of an ideal gas could be written just as a function of the temperature. K is 3/2 of nRT, right? And remember, as you have learned, that T should be used in Kelvin, right? Be careful with that. And so this relation is very important and very interesting because it relates the microscopic description, right? So in this term, you have the number of molecules, and then the mass of the molecules, and then the speed of the molecules. So this is a microscopic description. And on the other hand, we have macroscopic term that is just the temperature. And we have also seen that you can write this for just one molecule, so 1/2 m the square average. So this is the kinetic energy for just one molecule, and we can write this at 3/2 kBt. So kb is the Boltzmann constant, which can be written as the gas constant divided by the Avogadro number. So this is another way to write this, as we have seen in the last lecture. And so today we're gonna continue. There is one term that is useful to represent this term, this velocity square, the average of the square velocity here. If we take the square root, so we write this as VRMS. So this stands for root mean square, right? So you have the velocity, take the square, the average, and then the square root. So this is the square root of this term here. So we can write this using the formula 3 kBt over m square root. And so if you multiply the top and bottom by the Avogadro number, you can also write this as 3 RT over the molar mass, again taking the square root. So this is the RMS speed, and m here is the molar mass of the molecule. And so we can do a couple of questions to illustrate this. And so question, let's say that you have two ideal gases, two gases at the same temperature, but the molar mass of the molecules in gas number 1 are larger than the molar mass of the molecules in gas number 2. Then what about the RMS speed? So you see that because the RMS speed depends on the molar mass, and it is 3 RT over m with a square root here. So if the molar mass of gas number 1 is larger, then because this is divided by m, then we are gonna have that the RMS for gas number 1 will be smaller than the RMS for gas number 2. And then if we, what about the average translational kinetic energy per molecule? Right, so what about this? So this one, on the other hand, you have that the average kinetic energy of a molecule, we just saw that last time that this is 3/2 kBt. So it only depends on the temperature. And so since you have the same temperature, then that means that they are going to be the same, right? So the velocity are going to be different, but the average kinetic energy are going to be the same. Now, let's try another question. Let's say that you still have two gases at the same temperature, and they have the same total mass, but the molecules in gas number 1, again, have a larger molar mass than the molecules in gas number 2. So in this case, what happens to the total translational kinetic energy, right? The average translational kinetic energy for the entire gas. So that number is 3/2 nRT, right? So because they are at the same temperature, you may want to say that the average translational kinetic energy is going to be the same, but N is not necessarily the same here. So in fact, if you write this as a function of the total mass divided by the molar mass, then you will see that if the molar mass of molecules in gas number 1 are larger, then the average translational kinetic energy of this gas will be smaller. Now let's keep going. One more question. So those are all questions they are just conceptual questions to make sure you have a good understanding of the formula. So let's say that we have a gas in a box and the box have rigid walls so that the volume is constant, and let's say that we double the RMS speed of the molecules in this gas. Then what happens to the pressure? Does it stay the same, double, quadruple, decrease? So what's the relation between RMS and pressure? So you have RMS speed, that is 3RT, square root of 3RT over the molar mass. Now you can rewrite this using the gas law here. RT and RT is going to be PV, so 3 PV over NM. And so you see that if you want to double the RMS, then the pressure will be multiplied by 4. So correct answer for the pressure, it will be multiplied by 4. Now, side note about this RMS speed, right? This is not the same as the average speed, right? So RMS speed is the square root of the average of the squares, and this is not the same as just the simple average of the speed. And so if you want to be convinced of this, you can just calculate. Let's say you have only 2 molecules, V1 of 400 meters per second, V2 of 600 meters per second. So if I only have 2 molecules, then I can calculate the average very quickly. The average will be V1 plus V2 over 2, and that will be 500 meters per second. On the other hand, if I calculate the RMS speed, then this will be given by the square root of V1 squared plus V2 squared over 2, right? So this is the average of the squares, and then I take the square root, and you can calculate that, and you will see that you find 510 meters per second. So clearly these two are not the same, but the RMS comes naturally when we write the kinetic energy here as 1/2 V squared average for the kinetic energy of molecules. Now finally, those are all conceptual questions, but you also need to be able to plug in numbers. And remember last time when I asked you to plug in numbers, you realize that you make mistakes with units. And so this is something you should always be able to do also. So let's do a numerical question. What is the RMS speed of oxygen molecule at, say, 27 degrees Celsius, right? So for this you will need the molar mass of oxygen molecules, which is 32 grams per mole, and you will need the gas constant, which is 8.314 joule per mole per Kelvin. Now I could do this for you, but you would not learn anything, so I will let you calculate this, and you can post comments below this video. I'm not sure how I will do this, but we'll try like this. Okay, all right, so we continue. Now we're gonna talk about the heat capacity. So this is part 3. We already discussed that in the previous chapter. We mentioned that if you need to warm up a material, you're gonna need a quantity of energy Q that is proportional to the amount of temperature that you want to raise. So delta T, the number of mole, and constant that depends on the material, and that is the molar heat capacity. And so now we're going to discuss the heat capacity of a gas at constant volume. And we will show that for an ideal gas of point particles, then the molar heat capacity at constant volume, CV, is 3/2 times the gas constant R, 3/2 R. So let's do the derivation. So we have seen already before that the average translational kinetic energy of an ideal gas is 3/2 nRT. And so if we want to increase the temperature, if temperature changes by an amount dt, then the average translational kinetic energy is going to increase by an amount dk, which will be equal to 3/2 nR dt. And to do this, you're going to need some heat. And so the heat input that is needed for that is going to be dq. You're going to need to bring this energy, so it will be 3/2 nR dt. And by definition of the heat capacity, right, if you want to increase the temperature by dt, you're going to need an amount of energy dq that is equal to n CV dt. And so by combining these two results, you see that CV is equal to 3/2 times the gas constant. And so we can do the numerical application, right? If CV is 3/2 R, that is equal to 12.47 joule per mole per Kelvin. Now we can look at this table of molar heat capacity of several gases, and you can see that for monoatomic gases like helium and argon, we have exactly this 12.47 joule per mole per Kelvin. But if you look at other gases like diatomic or polyatomic gases like hydrogen, nitrogen, they are around 20 joule per mole per Kelvin, and polyatomic like carbon dioxide 28, hydrogen sulfur 25. So this model is only good at this point for monoatomic gases, right? So for diatomic gases, we're going to have additional energy that is going to be associated with some additional kind of motion, right? So for example, I'm going to have, if I take a diatomic molecule like this, I'm going to have some energy associated with the rotation along one axis, rotation along some other axis, and also some vibrational motion. And so those additional kind of motions are called degrees of freedom. And so the question is, what part of the energy goes into which type of motions, and also how each of them is corresponding to the macroscopic description, which is how they go into how they affect the temperature. And so for this, there is a theorem that is called the theorem of equipartition of energy, which states that each degree of freedom contributes to the same amount, 1/2 nRT to the total internal energy. So the theorem of equipartition of energy states that each degree of freedom contributes 1/2 nRT to the total internal energy. And so let's do an example. So if we have a molecule, we're going to have the translational degrees of freedom. So this molecule can move along 3 directions. It's going to have a speed along x, a speed along y, and a speed along the z-axis. And so we have 3 degrees of freedom. Each of them contributes from 1/2. And so the translational kinetic energy is 3/2 nRT. And this is the result that we already have used in the previous lecture. Now, because it's a molecule and not a simple atom, we can now have other degrees of freedom, like for example, the rotational degrees of freedom. So let's say you have your molecule here, right? It's going to be able to rotate around this axis, but also it's going to be able to rotate along this axis, right? And so this rotation, omega x and omega y, so that is 2 degrees of freedom for a diatomic molecule. And so one question is why we don't have an additional one for rotation along the z-axis, omega z, right? And so in fact there is rotation along the z-axis, but this usually doesn't change in ordinary collisions, right? So there is no way to transfer this energy, and so we can ignore it. So omega z does not change in ordinary collisions. So we only have these 2 degrees of freedom, and so for diatomic molecules, k rotational is going to be 2/2 nRT, right? That's for diatomic, right? If you have a polyatomic, let's say now I have a molecule like this, and so this time, this type of rotation along this axis, or along this axis, all of them are going to have to be counted because they can be modified during collisions, and so we are going to have 3/2 nRT corresponding to the 3 degrees of freedom rotation along x, y, and z. So that is for polyatomic molecules. And we also have additional degrees of freedom due to the vibrations of those bonds, right? So the vibrational degrees of freedom, and you know from physics 9a that the energy will oscillate between potential energy and kinetic energy. And so you have 2 degrees of freedom here, so kinetic and potential. And so that's going to contribute for 2/2 nRT, right? So if you add all of these, you would get 3/2 translational plus for a diatomic molecule 2/2 from the rotational, and then another 2/2 for the vibrational. Now, it turns out that the degrees of freedom can get frozen, and this is the results from quantum mechanics. You can see here, for example, for molecules of hydrogen, H2, you have the heat capacity that is 3/2, and as you raise the temperature, eventually the rotational degrees of freedom are not frozen, and so at room temperature we have around 5/2, and then on the other hand the vibrational degrees of freedom are completely frozen, and in fact the molecule dissociates before it reaches 7/2. Now let's do a question, practice question. So let's say you have two gases, 1 mole of argon of a monoatomic gas, for example argon, and you have another gas, also 1 mole, but of a diatomic molecule, say nitrogen. And both gases are at room temperature, and you warm them up, and you bring, for each of them, you add the same amount of heat. So plus same amount of heat. So what about their temperature? And so in fact, because one is monoatomic and the other one is diatomic, the temperature of the monoatomic gas will be larger than the temperature of the diatomic gas. And this is because the heat capacity for argon is going to be 3/2 nRT, right? So, 3/2 R. Whereas the heat capacity for diatomic molecule is going to be 7/2 because we have an additional 2 degrees of rotational degrees of freedom, and so it takes more heat to warm up nitrogen than to warm up argon. Another mistake here. And so the temperature of argon is going to be larger. Now this was for gases. Now what about solids? So part B, solids. And so for solid, we can view solids as a bunch of atoms that are linked together, and a useful model is this spring model of a solid, where you have spring connecting different atoms, and that represents the bonds. Now each atom can move in the 3 directions, so we're going to have for each atom 3 degrees of freedom. So each atom has 3 degrees of freedom, and so the average kinetic energy is going to be 3/2 nRT. But we have those bonds also, and so there will be also the potential energy, and so the average potential energy, which is the elastic deformation, is also going to be 3/2 nRT. And so the total is therefore going to be 3 nRT, and so that means that the heat capacity is going to be equal to 3R. And that is a rule that is called the rule of Dulong and Petit, that most monoatomic solids have the same heat capacity, which is equal to 3R. And so this is for an ideal monoatomic solid, and we can calculate this, and this is 24.9 joule per mole per Kelvin. Now we have already seen this table before with the specific heat and the molar heat capacity, and you can see that for the monoatomic solids, like for most of them, like aluminum for example, 24.6 joule per mole per Kelvin, copper 24.8, iron 26, lead 26. So for most solids, this is a pretty good model that explains the heat capacity. And so essentially it means that it doesn't depend on the mass of each and every atom. It only depends on the number of them. And so if you consider this as a per atom basis, then the same amount of heat is necessary to raise the temperature, right? Even if the masses of the atoms are different. And same as for the gases, turns out that this rule works very well, but there is a problem. When you cool down and you reduce the temperature, heat capacity actually drops. And this was a problem that took a while for physicists to be able to explain that, and this is explained only by quantum mechanics. And so at low temperature, the Dulong and Petit prediction is not working, and the heat capacity of solids is going down. Okay, so at this point, you can do all of the problems in the homework, and also the practice problems, the additional ones that I had given that you could not do before without knowing this part about heat capacity and the theorem of equipartition of energy. Finally, we're going to discuss 2 more parts quickly. We're going to come back to this concept of the molecular speed. So that is part 4, molecular speed. And then we're going to discuss this effect on phase transition. So molecular speed. So first of all, how can we measure the speed of a molecule in a gas? So you have this conceptual description in your book. So I took the picture from the book. So let's say you have a gas that has some moving molecules inside. You make a hole, and so you're going to select some molecules that have a particular direction. So you have some kind of screens here with a hole in it, and then you have a vacuum chamber. So the molecules that have a certain speed along a certain direction, they are going to go straight through this vacuum chamber, and you have a set of rotating discs with a slit so that you can select only the molecules that have a particular speed are going to be able to go through the first slit and the second slit, and all the molecules that have a speed that is either too fast or too slow are going to end up on this wheel here, and they are not going to be able to make it through. And then you have a detector that is going to measure the molecules that are arrived on the detector. And so this way you can get the experimental measurement of the speed of a molecule. And so what is the probability that a speed is exactly, say, 100 meters per second? In fact, the probability that the speed is exactly a certain number is 0, right? There is no chance that a molecule is going to have exactly 100 meters per second velocity. It might be 100.01 or another number, but the probability to be exactly a certain number is always 0. And so we cannot talk about probability of having a certain speed. Instead, we're going to discuss a new mathematical concept that is the concept of a distribution function, which is also a probability density function. And so if you have n molecules, and you can call dn the molecules having speeds between v and v plus dv, the distribution function is going to be defined so that dn is equal to n f of v dv. So in this formula here, f of v is a distribution function. So what this means is that it's a density of probability. So if you multiply by dv, then you get the probability. So f of v dv is the probability of having a speed between v and v plus dv. So essentially, f of v is a probability per unit of speed. Right, and so if we represent this on a graph, f of v as a function of v, it's gonna look a little bit like this. And so we will have a maximum here at a certain speed vmp, so that speed would be the most probable speed. And if you take two speed v1 and v2, then the area in this curve here, the area below this curve, would represent the fraction of molecules with speed between v1 and v2. And so if you're given this function, then if you need to find the most probable speed, then this is when you have a maximum, and so the derivative is 0, and so you're gonna have to just solve the derivative df over dv equals 0, and the solution will be the most probable speed. If you need to find the average the average velocity, then this will be equal to the integral of v fv dv. Right, so you take each velocity multiplied by the probability to have this velocity, and you sum all of them, and so you get the average velocity. That's how you calculate average. If you need to calculate the average of the square of the velocities, then you can use the same technique, but in this case you're going to take the square of the velocity multiplied by the probability vf v dv. And if you're able to calculate the average of the square, then you can calculate the RMS speed. So that would be by taking the square root of the average of the squared of the velocities, right? And for the molecules in a gas, this function is called the Maxwell-Boltzmann distribution. And I'm gonna give you this equation here. You don't have to remember this, of course. So this is equal to 4 pi m over 2 pi kBt to the power 3 half v squared, and then exponential minus 1/2 m v squared over kBt. Okay, so this is the Maxwell distribution function, and so from this you can calculate the most probable velocity, which is 2 kBt over m square root. You can also calculate the average speed, and that is 8 kBt over pi m square root, and the root mean square RMS, which is 3 kBt over m square root. And this is the same result as obtained before. Right, and again you see that the average velocity and the RMS speed are not the same. Now here you can see this distribution function depends on the temperature, and you can see as the temperature increases, this curve flattens, and the maximum is also shifted to higher speeds, right? So if you increase the temperature, the most probable velocity is going to be higher, and there will be a broader distribution of speed in your gas. Now this is also useful to understand phase transition, and so for example the liquid gas transition. So you can imagine that a molecule will need a certain speed to escape the surface of a liquid. It will need a certain amount of energy, and so if you increase the temperature, you increase the number of molecules with large speed and large enough energy to escape the surface of the liquid, and so they end up in a gas above the liquid. Now on the other hand, some of the molecules in this gas are going to get trapped into the liquid as well, and so you have an equilibrium between the liquid and the vapor that will take place. And at the same time you see that the molecules that leave the liquid are the ones that has the higher speed, and so that means that the molecules that are left in the liquid, they're gonna have lower energy on average, and so that gives you an explanation at the microscopic level of this cooling that happens for the liquid when there is evaporation, right? So evaporative cooling described microscopically. Now a few more words, part 5 on the phases of matter. And so this is mostly for you to be able to read a phase diagram. So we've already shown this phase diagram several times in this class in Physics 9B. So this is the phase diagram of water, pressure as a function of temperature, and you have different regions. At low temperatures you have this solid region, and then the liquid region, and then eventually the gas region. And so to read this at a given temperature, for example, if you are at 1 atmosphere and you increase the temperature, at some point you're gonna hit the normal freezing point here at 0 degrees Celsius, and so you're gonna have the transition between solid to liquid. Then if you continue to raise the temperature, you're gonna meet this line here, transition line between the liquid and the gas, and this is the boiling point. And you see that the freezing point and the boiling point, they will be different as a function of different pressures. And the point where the two lines meet is called the triple point, and so that point has a very specific pressure and a very specific temperature.